Hey, Eric.
Okay. I gotta talk to first. He made a move yesterday, so he messed with the board. He made a move.
Rachel, Debbie Down syndrome.
That's
bad.
That's
That's bad.
So I gotta get
Emily, do you?
Done.
I was so excited about that.
I only can play 3 quarters anyway, so.
No.
I only can play 2 quarters, so I might play.
You do not know how hard I'm actually.
No, actually.
Come on up.
Oh, those
You can
keys are weird.
pour it on me,
Huh?
just not
Those
on
keys are weird.
I know, it looks like I'd snap if I tried.
You can pour it.
Push down too hard.
You can pour it on me. No.
Oh,
Actually, do.
Did that bother you the whole class, right?
a little bit, yeah.
You're so I'm gonna feel like
I'm tired too. I'm tired both shooting time together.
I
It's
should.
too
Or pull this one during here.
No, that's so sad. Plus, the weird, I was gonna say what you're doing. Stop. No, stop. No. I was going like this, and I saw my computer. And I was just kind of like chilling here, pushing.
You don't know.
Honestly, I should probably ask my boyfriend, but I'm too scared to. He hasn't asked me to his homecoming. His homecoming is next week. I don't dress. Mason City is like super like tight and like normal. I don't got that. Actually, I do. I'm wearing No! I know you need to ask him.
Carly, there's a cooler in the back of my truck for a reason.
Huh?
There's a cooler in the back of my truck for a reason.
I should probably definitely ask him, but I'm just too scared to, which I don't understand why, because everything was right, so.
Get a box of donuts and then be like,
Carly,
"No, it's not
stop
good."
being a big pussy.
You know what? Shut up.
Riley, I'll leave that with you.
I was too scared to hold his hand. So, I mean,
I'm gonna be an individual speech, not group speech.
well, you're in speech.
What?
Hey, Brian. This is last year's
Okay, we have Allison here today. Where's she at?
Yeah, I'm blowing up my Snapchat.
Okay,
I'm
if
blowing
you
up
want
my
to sit up there,
Snapchat
you
this
can.
morning.
If you want to sit where she
On my story?
is.
That was last night.
Okay, hey, let's
That's
take a
fine
look
for
at
all
some of the
photos.
let's take a look at
That's fine for all.
some of the notes we did yesterday. I want to pop that that PowerPoint back up on the board just to make sure we can discuss. Then we are going to go through homework problems right now. So if you did anyone turn in page 50 yesterday? Okay, I'm going to hand those back. That way we can take a look at it, right? So page 50. All right, so let's see. Jared, you're up. You can grab that. Ashley, you can grab yours. I think that's pretty much about it. Anyone else turned in that they know for sure? Okay. Hey, let's talk about number 5. Number 5 and 27. That's the 2. Okay. Do you need your book for this? Do you have your homework right there? Hey, you might want to go grab it then. We need it almost every single day. All right. Okay. All right. So again, what we're doing here today, we're going to finish up the main part of the notes on 1-6 today, which is on the polygons. But before we do that, we got to make sure we do a homework. We're going to review that homework problem. So review homework page 50. We're going to look at number 5 and number 27. And once we're done with that, then we're going to go into that PowerPoint. Because what we need to finish today on that PowerPoint is we need to get to the triangles. Okay, because on the PowerPoint, we discussed the different polygons, right? We talked about the definition. we talked about the types, we talked about the classifications, but today, our main goal on this classification idea is we need to discuss triangles. And then if we have some time, we're going to do the construction stuff with triangles, drawing the perpendicular angle, the 60-degree angle. That should go nice and neat. Then we're done for the day. So very, very nice, very easy. Okay, so, but I do want to get to that, but I don't know if we'll get to this construction idea. Some of the other classes didn't get to it, so if we have constructions here, we'll have constructions number 3 and 4 today. So we'll see if we get there. Okay, so I need somebody with their book open. I need somebody to read problem number 5 for me. Just say it out loud slow. I'll tell you when to stop so we can discuss. We're doing number 5 on page 50.
Lines X and Y intersect to form adjacent angles.
Okay, stop there. Okay, so X and Y, whatever these lines are, they're crossing to form adjacent angles. Now, what does adjacent mean? Yeah, right next to each other. So, do you agree that these two angles are next to each other?
Yes.
They're adjacent. Okay, that's what they're basically talking about. Okay, so read slowly, keep going.
Angles 2 and 3.
Okay, all right. So these were angles 2 and 3. Now, here's the weird thing. I don't know which one's 2, which one's 3. It really doesn't matter. What I'm betting on is what Cook's about to read will explain which one should be where. Because I don't know if 3 is supposed to be the bigger angle, if 2 is supposed to be the smaller angle, or vice versa. That type of thing. So, okay, keep going. Let's hear what they say.
If angle 2 equals 3a minus 27, and measurement b equals 2b plus 14, find the values of a and b so that x is perpendicular to y.
Okay, so my picture's slightly off. So, were these right? 3a minus 27, 2b plus 14? Those are the correct things?
Yes.
Okay. What they said is that we want to figure out what will make these two angles work, like what will be the values for a and b, if these two lines, x and y, turn out to be perpendicular. What does perpendicular mean?
90 degrees.
90. That's what you need to realize. We have 4 90-degree angles here. That's how you solve. Because we want to make this picture look perpendicular. So, guess how you solve for a? What's 3a minus 27 equal to? 90. It's also equal to the other angle. I know that. They are actually the same angle. Okay? Because they're both equal to 90. But I wouldn't want to set these equal right away. I know you could. You could literally set them equal because they are equal because they both equal 90. Or you could add them together to make 180. Those are different ways you could solve this problem. I've definitely said that in past, that you could add those together or set them equal and set up your both equations. I personally think that this would be the easier route, but it is possible to do the other way. I'm not going to go through that today. I might make it up tomorrow, in future lessons we might come back to this problem. That's number 5, because there's different ways to approach it. Okay, but this is how you solve it. I'm going to add the 27 across. So if I add 27 to the 90, I get 117. And then if you divide by 3, that goes in there 3, that brings down 2 and 7, so it's 39. Okay? Is there any questions with that? Is that what some people got?
Yeah.
I know that the odds are in the back. Question?
No, I got that.
Okay, perfect. So, okay, that's good. So at least my math is correct. Now we got to go to the other angle because we do need to find B though. Okay. All right. So we do need to find angle B, which is the 2b plus 14, and we got to solve for that. So 2b plus 14 equals 90, and we got to solve that thing out. Fred, don't worry about it. Take your time, buddy. Come on, let's go. You're on your own little mission today. All right, so 2b plus 14 equals 90. So I'm going to subtract the 14 across. Okay, and when you subtract it across, you should get something like 76. If I subtract the 14 over to the other side, and then you're going to divide by 2 here. And if I divide 76 by 2, that goes in there, let's see, 3 times the 6, bring down the 1, that's 38.
Are you serious?
All right.
So what happens if it's not like perpendicular?
If it wasn't perpendicular, that would be a completely different problem. You'd have to solve it by the method I'm hinting at that I'm going to show at a later date, which would be a system. That's what we'll call it, okay? We'll bring that up at a later time. Okay, any questions with number 5? Make fixes if you haven't got that, Okay, that should be your answers for 5. It looks like a lot of people are getting that. Plus, it's an odd. It's in the back of the book, so you could have double checked. Okay, but let's move on. Let's try number 27. Okay, all right, 27. Now I need somebody other than Cook because he already got the first one. So somebody else read number 27 for me. What do we got?
I'll do it, but I don't have my book.
Well, can't be you then. Common sense. Okay, somebody else now.
Hustle for it still.
Somebody, whoever starts reading, whoever's got it.
Uh-oh. Uh-oh.
Bannister's got it. All right.
The measure of the supplement of the angle of an angle is.
Okay, so the measure of a supplement. What does supplements mean?
180.
Yeah. So supplements mean you have two angles, basically a linear pair. And when you add these two angles together, you make 180. That's what a supplement means. That's the setup. That was the first 5 words there. Okay, keep going. The measure of a supplement is?
Of an angle is 40 more than 2 times the
Okay.
measure.
40 more than 2 times the measure. Now we're going to have to put something in here. 2 times the measure of something, which is going to be more complicated. And what does it say?
Of the complement of the angle.
Ugh.
Find the measure of angle.
Okay. So this spot here is the complement of this angle x. X is over here. This thing, what's in here, this is 40 more than twice its complement. Okay, let's talk about what complementary angles mean. 2 angles add to make what? 90. So if this angle's x, the other angle, its complement, is 90 minus x. Because how I know that? If this is 40, that's 50. Because it's 90 minus 40. That's how it works. That's what I'm plugging in right here. I'm plugging in a 90 minus x.
But that's not 90 degrees.
No. It says that this supplement, however this works, this angle, that supplement, is 40 more than twice whatever the complement of the other angle is. They somehow put it in a relationship to its complement to make this thing work. So, what do you get when you add both of these angles together? 180. Okay, so 40 plus, and this is the weird part, that 2 times 90 minus x, that's one angle, that's that one angle over there, plus the other angle, that's equal to 180. So I'm adding these 2 pieces together. I'm probably got my drawing wrong. Probably what happens, this stick here that I've drawn, this ray, probably should have been going maybe this way, because the x is probably the smaller angle. This one looks like it's obviously the bigger one. Okay, now, the reason why I bring this up, why I thought this is difficult, because I read it yesterday, I was like, whoa, it's saying supplement and complement the same problem, which are completely 2 different things. And the idea is that it has this part. This is ugly, this part. How do you actually do this? Exactly, yep, you distribute. You take the 2 and you multiply it through. Okay, I remember when in elementary, my teacher was Mrs. Penny. You know Mrs. Penny? She was my teacher when I was in like 4th grade, 3rd grade. Well, when she taught distribution like this, she called it turtle method. It looks like a little turtle. Totally silly, you can see it. It's silly, but I remember it. So you were taking the 2 times everything in here, right? So it's very obvious. So it's 2 times 90, which is 180, and then it's 2 times the x, which is 2x, right? And x equals 180. All right, so that's how you do the item up front. It's distribution, but how distribution works, it looks like a turtle shell because you're taking the 2 times each item. Okay? Does that make sense how I got the 180 and the minus 2x? I know it's silly, but that's the way Ms. Benning taught it, and I like it, so I use it from then on. Okay, so now at this point, I'm going to add, move things around, solve it out. So if I add these 2 things together, I get 220. Add the 2x, the plus 1x equals the 180. I'm going to move this 220 across. And what happens when I move it across?
Subtract it.
Subtract it, right? So we've got to subtract that thing off over here. So I'm going to literally be subtracting that 220 over when I move it. So this is what it's looking like. Okay, at this point, what's a negative 2x plus a positive 1x?
X.
Negative 1x. Because it's negative 2 plus a 1. That's negative 1. 180 minus 220. Negative 40. Yep, you're absolutely right. And now the last step, we divide by the negative, right? So you divide by the negative 1. Yep, and that's how you get positive 40. 40, the negatives would cancel to make positive 40. Which I believe is the same answer in the back, correct? Right? Yeah, the answer in the back. So, is that what everyone's getting? If not, make fixes. That's your answer right there. Now, if you had to take this 40 and plug it back into that mess, okay, then that means this is 40. And that means if I were to plug it in here, just common sense, this has to be 140. This has to add the other one. I don't think they asked for that, correct? They didn't ask for the other angle? Okay, there you go. They just asked for the, I think, find the value of that, so there you go. Okay, that'll help you out with 27. I know that that problem is ugly. I knew we had to cover that one. So, okay. Any other questions on that for problem number 5? Okay, this homework assignment is due at some point today. I don't care if it's at the end of the day. I don't care if it's right now. If you're done, you can put it in my basket.
No, yeah, because I haven't checked James. It's all multiple choice except for one. It's an essay question. Yeah.
Okay. Turn up lights here. Okay. Okay, this is the PowerPoint we started yesterday. If you were not here, this is what we kind of talked about. The video should be online at some point today. I think I posted it to YouTube, but I forgot to attach it to my website. It'll be on there today, so if you want to watch, I'll actually attach this PowerPoint to that, plus the video that we recorded yesterday. So, pretty straightforward. It's page 50 is due today. I want to make sure that, but we gotta get through this PowerPoint and get to the triangle idea. Once we get through this triangle, then we can get to the constructions, which I'm hoping we can get to today. Okay, and I'll explain as we go what we're gonna try to cover with this stuff. Okay, polygons. I'm gonna blitz through some of these slides because we don't need them all, because we've already talked about them. Like polygon, we talked about how to draw them, right? The polygon was the definition of polygon was many angles according to your textbook. It's stupid. That's the dumbest definition ever, but it's a shape that has angles in it. Now, more specifically, if you want to know how to draw them, what I gave you yesterday, my bullets were, number 1, you had to have coplanar segments. So you had to draw segments, and they had to be connected, right? And they had to be on the same flat surface, whole common sense, right? You're drawing something on a piece of paper, marker board, it's on one flat surface. So that's how you draw. Now, there were stipulations for those segments. Like number 1, when you draw a segment, it has to be connected to 2 or more others. So if I get down to this part here, if I draw a segment here, this segment has to be connected to 2 or more others. So minimum 2 others. If that stick's connected to 2 others, what would that shape be?
Triangle.
A triangle, right? That's your minimum shape, and we talked about that yesterday. Now, it could be more. I could have another one in here. That's fine. But it has to be connected to 2 or more. So this one has obviously more walls than just the 2 others. Okay? Now, what we also talked about on step 2, that when you draw those segments and they're connecting, they had to meet at the end points. You can't have them like cross in the middle, something like this, where, you know, I'm going to draw a 4-sided figure, but you can't do the bow tie object because they're not crossing at end points. They cross in the middle. Now, somebody asked a question yesterday, I think it was like Meg Eastman asked me in like period 7, well, what if you put a dot in the middle? Like, what if that's an end point? It still fails because of step 3, that these segments can't be in a straight line with each other. Okay, because this would make a straight line. And you can't have that. No, none of those things can be in a straight line. Now, I did have another question. It was, I think, period 8. Well, could you do something like this, where they're not in a straight line with each other, but it made kind of a random shape, right? Well, the idea is that the step 3 actually extends to say that that no segments with common endpoints, are not collinear. But it also says, and I didn't state this, that you can't have multiple segments here that all have the same endpoint. They all have this endpoint. You can't have that. So I didn't state that in the PowerPoint because I didn't think it was going to be an issue. But somebody brought it up yesterday, so this can't work. That is not a polygon. So, all right, question in the back?
The bow tie deal?
Yeah.
Could you put 2 endpoints or endpoints in between?
Something like, something like this maybe?
No, like, well, yeah, that's obvious. Like, yeah, that's a polygon.
Yeah.
Sculpted. I don't know. All right, yeah.
I'm interested. Yeah, draw it over there in the white. Right over there. Oh, okay.
Getting up here on the wall.
Like, actually, like on the board. Like right in the light area. Give you the one marker that doesn't work. Alright, go. Alright, let's see.
Like, like 2 dots like that.
Oh, no. Because it's still the same situation. That,
Well, technically, wouldn't there be
there's a segment connecting them, but the problem is, like, you would still have this issue where you don't have an interior. I don't want that idea where you have a line like this in the middle with a bow tie going out. Because now what's happening here is that these segments all have common endpoints, and that can't happen. That's what stipulation 3 says. Even though they're infinitely close together, right? It's still the situation like this if I extended it. Multiple segments are hitting the same dot, and that's this. No segments with common endpoints can keep going. Yeah, that's a good idea, right? All right, that's good. See, those are the types of things. Like, do you have an idea? Throw it out there. That's helping us figure out these definitions. I like it. Okay. All right. Does that help you out?
Yeah.
Okay. All right. Any other questions, comments? That was good, though. All right. Let's keep going here. One of the other words we talked about was those corners, right? We call them vertices, right? A vertex, a point of intersection. That's why I put endpoints in air quotes. It's actually called a vertex, right? Vertices are plural. Then we talked about sides. A lot of the time the book refers to them as sides of your polygon. I call them edges. I call them segments. So don't be confused if you ever see that. Okay, any other questions with what we talked about yesterday? Okay, then we discussed that there was 2 types. There's convex. There was your definition. We talked about concave. Basically, the idea was convex is a big fluffy pillow, very open on the inside. It's billowy like a pillow, open. As opposed to concave where there's cavities. Something like this, where there's a cavity on your problem where this is a cavern. It's like a cave. It's a mouth. It's a cavity. And so the idea here is what these definitions are telling you to do, and this is the instruction I gave you yesterday, was you draw a line connecting interior points, and if that line crosses the outside of the photo, it's not convex. So this idea is that line crossed the outside when I draw a line connecting interior points, so it's automatically concave. And if you could put it in a spot where it could do that, it automatically makes it concave. This type is the one that I don't want to draw. I don't want to draw those for these other, when we get to these classifications. I don't want to draw that type of picture. I want to draw these open, symmetrical kind of looking things. Okay, any comments, concerns about those 2? Okay, now, we'll discuss polygons the classifications here. Triangles is the first type. We already said that, right? Here's a triangle. Yesterday, did we discuss that I could put lowercase letters?
Yes.
Okay, perfect. Greek letters in the corners. Quads are 4-sided figures. Any type of 4-sided figure. There is, I think, 6 types of quadrilaterals. there's 7 types of triangles. We're going to focus on triangles today. That's going to be our main one we're going to discuss. Quads will be Monday, so that way we can separate. This is a lot of part of the geometry that we learned this year. We learned properties about these. I discussed that yesterday, like trigonometry is literally the study of triangles. That's what trig is. And so we'll focus on the major properties for these two objects. Now, obviously, the formulas that we eventually get that apply to all of them are like area and perimeter, and eventually when we get to 3-dimensional objects like volume and stuff. But these are the ones we focus most of the year on. But don't get me wrong, we do hit the other ones at some point, especially with like diagonals or interior angles. We can control those types of things. Okay, Pentagon is a 5-sided figure. We talked about the building in Virginia. We talked about a hexagon. The key letter there is X. That's the same letter in 6, so it's 6-sided. Looks like honeycomb. We talked about heptagon or septagon. This is, I think, the Roman. This is the this version is the Latin, and they're found in different textbooks, so I don't care which one you pick. Octagon is 8, obviously. It looks like a stop sign. We talked about a nonagon or a ninegon. I like nonagon. I think your book refers to it as a ninegon, though, I'm pretty sure. Decagon is 10. That's literally the Latin word for 10. Deca is the metric system, right? 11gon or hendecagon. Hendecagon is Latin for hen, meaning 1 more than a decagon, so 1 more than 10. And then dodecagon is 2 more than 10, so it's 12. After that, what we talked about was anything below that is basically 13gon, 14gon, 15gon. Okay? All right, any questions, comments, concerns about the main ones here? These are perfect words I can put on the next chapter test. Or like the one that we have, next Thursday or Friday or something like that, which we'll get a review on Monday for that. Okay. Let's go on. Today's topic, we need to focus on triangles. That's what we need to focus on today. I want to make sure that we get all the different types, you know how to draw them, because when we get to the constructions, these fit perfectly with triangles. Like, we're going to learn how to draw perpendicular angles, which are 90-degree angles, and 60-degree angles. That's what we're doing. Okay, any questions with that? Okay, all right, let's move on. Here we go. Triangles to start with. Okay, again, how we classify polygons, why we have this classification system, is by the number of sides, the number of edges. So when we talk about triangles, tri is the key word there, the root word is 3. So there is 3 objects here, A, B, and C. Okay, now, how many sides are there? 3 edges, right? How many vertices are there? 3 angles. So literally the word tri is very appropriate, meaning 3. Okay, now when you describe triangles to somebody, this is basically how you describe it. You describe it by its side lengths or by its angles. That's how, like, if you didn't know the name of the objects, that's how I would, like, visualize that picture. That's how you classify triangles. It's by those 2 categories, side lengths and angles. They have names under these. Those are the names I want you to know. So anytime you look at a picture of a triangle, there is probably 2 names that can go with that thing. That's what you need to realize. 2 names fitted appropriately. Okay, it's side lengths and then describing it by its angles. Those are the ones I want you to know before you leave here today. Those are the ones we're going to spend some time on. And if we get time, we're going to do constructions. If not, no big deal. We'll just continue on another time for that. Okay. I know some of you are like scrambling to write this, so it's fine. We're going to start with the side lengths first, and we'll go through the names for triangles with that. And then eventually we're going to talk about the angle measures. Okay. Anyone still need that? Straightforward. All right, let's start with the side length. So I'm going to put that back on the board. But we need to go through the different names here. Okay, so triangles by its side lengths. So here we go. First one. It's called scalene. Now, anyone happen to know what scalene means? And there's a common error that people think. So I'm going to squash it right now if I hear it. So, scalene, what do you think it means?
Isn't it all 3 sides are the same?
Nope. Close. Really close.
All 3 sides are different.
Different, yeah, all 3 sides are different. This is exactly a picture of scalene. If they leave it blank, like blank, no markings. We assume that all three sides are different. That's safe to assume because we're not assuming anything specific. They're all different. Now, what I prefer, because I know you can leave it blank, but what I prefer is you actually put marks on that. What I mean by markings, marking that the three walls are different, you would do this. You put little hash marks. That means the three walls are different. It does not tell me which one's the biggest. No, the mark 3 and the mark 1 doesn't mean one's smaller or bigger. Doesn't mean any difference. It just means that they're different. Does that make sense? Because it didn't matter where I put the 1, 2, and 3. I just went clockwise. Okay, I prefer that when you're describing scaling that you actually put the markings. The book tends to leave them blank, so that's how you know. Okay, any questions with the word scalene? For some reason, people think this means something different. It means that they're different. Okay, they're all three different for the side lengths. Doesn't say anything about the angles, which we'll come back to here in a minute. Okay, second type. I already heard it. Somebody's already whispering it. Isosceles. Okay, what do you got?
Show the sides of this.
Boom, two sides are the same. Two sides are the same. Two sides. Now notice, my picture. The markings have to be there for isosceles. I'm notorious for spelling it wrong. The only reason it's spelled right now is because the computer auto-corrected it. I always forget the stupid letter in the middle, the S. I always forget the second S. I always forget it. So, just know, this is the correct spelling of isosceles for once. Now, the actual picture of it there's names to this thing. Now, it's only talking about its sides. That's all isosceles is talking about. But the actual items here that are the same, they have the same marking, these are actually called the legs of the isosceles triangle. The legs that match. Okay, bless you. The bottom of this object, which is the random third wall, that is actually called the base. It doesn't matter how you flip or oscillate this triangle up and down, doesn't matter. The base is always the random third wall. I don't care if the base is on the top, it's still the base. Okay, now, there's things we are going to learn. This is a big triangle. There's a ton of properties that apply to isosceles. One of the main ones we learn, like one of the first ones that we're going to learn, is that the certain angles of that triangle are equal. That's one of the first things we learn. Because if the walls are the same, it forces angles to be the same. So that's what you need to realize. Now I'm going to label some of these angles. So on an isosceles triangle, the top angle is called the vertex. The bottom two angles are actually called base angles. Base angles. And there's two of them. And what do you think that's important about the base angles? They're the same. Yeah, the angles that touch the base. Okay, that's something we'll eventually learn. I'll talk about why later. But that's something I want you to know the terminology in case you ever need it. Okay, now the third type of triangle by its sides is called equilateral. And as you can tell, the three walls are the same. Because if you go to the root word of equilateral, equus meaning equal, and laterals are sides, equal sides. It's self-explanatory. Now, what can you tell me about the angles of an equilateral triangle? They're all the same. Because if the walls are the same, the angles are the same. That's just something you need to realize about triangles. The walls are in direct relationship to the angles that are across from them. So when the walls are the same, the angles are the same. So in fact, I could actually put the angle markers in here, because they're all the same. So in fact, instead of calling this an equilateral triangle where the walls are the same, you could also call it by the second name, which I don't have printed here. It also could be called an equiangular triangle. Equiangular. Now, the thing that's scary about me telling you that is that those two words mean completely separate things. On a triangle, they go hand in hand. But on everything else, they mean different. Because equilateral just means the sides are the same. Equiangular means the angles are the same. They just happen to be the same on this picture. Now, what did I talk about yesterday? If the walls are the same and the angles are the same, we called that picture by a different name. It was called something with an R.
Right.
Nope. Somebody's.
Right.
Nope, not right.
How about
R-E.
Right.
Well, heard it.
Right.
Regular. Thank you. Somebody said it. I don't know who. Okay. So, alright, so it's regular, right? This equilateral triangle is actually a regular triangle. Remember, the word regular in geometry means the walls and angles are the same. So you have to mix both of these words together. That is the most special type of triangle you could have. Now, the thing that I need to make sure of, that these two words here, they mean different things. Don't combine them together. Because if I go to a four-sided figure, a quad, I could have a quad that has the same walls, but the angles are different. The angles could be different. So that's equilateral, but not equiangular. So you need to make sure that you realize these are two different separate things, but on a triangle, that one just happens to be that way. Okay, any questions with the four words on the board right now? And I erased the word regular, sorry. Okay, let's talk about the triangle by its angles now. And some of you have already said the type of triangles already. Okay, these markings. All right, so triangles by its angles now. Now again, remember these three words because I'm going to come back to them here in a minute. Okay, so angles, there's triangles by its angles. The first one is called an acute triangle. What do you think acute means?
Less than 90.
Less than 90. Okay. Yeah, those are the second type, right? So an acute, all angles are less than 90. Less than 90, right? So if you can see this, these are all different, they're all smaller. So, in fact, if you look at this picture and all the angles are less than 90, there was a couple on the other slide that I showed you that were also acute. Now, if you look at this marking of this triangle, marking that the angles are different, this is how you do it. All the angles are different. So if all the angles are different, what else could you call this triangle? It also leads to the fact that it is scalene. Because scalene, the walls would have to be different as well. So right now it's acute because all the angles are small, but eventually we know that this is also scalene because the walls are different. Okay. All right, any questions about the word acute? Most people know it because it's based on angles, and that's what we call angles, acute angles, right? All right, now, Fred, you even said it. What's the second type? Right. Yeah, it's a right triangle, right? The idea is that on a right triangle, you have a little box in the corner, one 90-degree angle, and only one. I will come back to that idea of having a triangle where we can put two 90-degree angles in it. We'll discuss that. I believe it's like the middle of chapter 3, or chapter 2, I mean. We'll come back to this concept where I try to mess with you a little bit when we look at this picture. Okay, so one right angle. Now the walls could be the same, I have no idea. They could be all different. So this could be isosceles, it could be scalene. I have no idea. Okay, that's a right. Most people know it. Only one right angle. That's actually a property of math. And obtuse. What do you think obtuse means?
Bigger than 90.
One angle bigger than 90. For some reason, this triangle is the hardest one for people to understand. There's not a lot of properties with obtuse, but it's the way that people, like when they look at the picture, they don't realize it's obtuse. This one's obvious, right? This angle is way larger than 90. But when I suddenly flip it over, now for some reason, people don't understand it's still obtuse. Because they always do the thing where they like turn their head and they're looking. It's obtuse. Just get over it. I don't know why, but you just can't see that.
Okay, but that one looks more 90 degrees.
This one?
Yeah.
Yeah, it's not. It's that same one.
I don't get it.
So, yeah, it's just an optical illusion. People's brains can't handle that. So, when you turn it over, I don't know why, it's the hardest one for people to spot. Okay, now, these three words work in tandem with the other three. Okay, and it's not side to side. It's not like the last one, like equilateral goes with obtuse, because that's not true. They just, every time you look at a picture of a triangle, there's always two words that go with it. You pick one of these three words, you pick one of the other three words we talked about. That's what you just do. So we could call this scalene, isosceles, or equilateral, and one of these three. Typically, we try to stay away from the word equiangular and regular. We try to use one of these. Okay, are we good with the triangles?
Yes.
Okay, question.
Do segments have to be straight?
Segments, yes, they do have to be straight. They can't be curved.
So you couldn't make triangle. Well, you could. It's just it wouldn't be considered a polygon if you made it like the base of it would have a curve.
Yeah, it wouldn't be considered. So. Okay, now, like what I was hinting at, we talked about triangles today. Monday, we're going to talk about quads. There's 6 types of quadrilaterals. Okay, and then Monday we'll also talk about circles. Circle is the only shape we did not talk about today because a circle, like you were saying, a curve, is not a polygon because polygons have segments. They have straight edges. But a circle is a curve. It's a conic section. It's part of a cone. So we're going to talk about those on Monday. Okay, you have the rest of the time today because we're not going to get the construction. You have the rest of the time today to kind of work on this assignment page 50. If you have it done, you can turn it in the basket up here. It's due at some point today in my basket right there. With your name on it, date, period number, page number.
Hey Ward,
What are you gonna do?
I made a fire play in chess.
You made a what?
Fire play.
With a fire play.
It's like it's a great play.
Is that on my board right now?
What?
Is that on my board right now?
Huh?
I wanna look at this chess
I
game.
mean, you don't know. You obviously know. Actually, Ty, if you pull on this one, what's it do?
Don't tell her.
Hi.
How don't you know this?
Pull it really hard.
Oh, I want to.
Just do it.
Well, because it'll ruin my shoe.
Just do it.
No, is it like, will it make this not really tight? No.
I'll do it.
No, because then I'll be able to untie them. No.
Oh, I'll show you how.
No. Do it on your own shoe.
These shoes are way too old for you to try it.
No.
Just doing it try to fall off. It's too hard.
Why? Does that really bother you?
Next time she does it, try grabbing it with quick six.
Which is totally wrong because I'm slow enough.
I'm slow.
Now everyone thinks I'm old when I'm shot.
What'd you do? What's your word?
I drive a different vehicle on page thinks I roll my shot.
I would too. What do you drive your car?
I drove like a motor one yesterday. You look confused then.
We have like a couple minutes here.